Hi guys, today's topic is finite state machine. So let's start with the topics. So, so this is the finite state machine. So far we learned about uh, stateful components. So far we learned about the combinational logic, where the output computed directly from the inputs, and okay, and the system has no internal state and nothing depend on the past. Like we have like n number input, and then we have some combinational circuit, and then we have m number of output. It couldn't record the data, it couldn't build a stateful circuit, and it can't there is no state and hold device. So what we need to do, we need to record the data with a build a stateful circuit and a state holding devices. So therefore we need to know about the sequential logic and finite state machine. Now the goal for today is to know about the finite state machine. How do we design logic circuit with a state, and then the type of finite state machines, and then examples, one for the Mealy machine, other for the Moore machine. So let's start with those. Now first come what so first, how to design a logic circuit with a state. So before starting, we need to know what is finite state machine is. The finite state machine is an electronic machine which has external input, externally visible output, and internal state. So we can't see the internal state, we can see only the external inputs and external visible outputs. And output and the next state can depend on the inputs and the current state. So this is the abstract model for a finite state machine, where the machine M is S, the function of S, I, O, and delta, where S is the finite set of state, I is the finite set of input, O is the finite set of output, and delta is the state transition function. And next state depends on present input and present state. Now this is the automata model for a finite state machine. So it has some registers to hold the memory and some combinational logic to make the design, and so here we have input for this external world, output for the external world, and internal state. The kind is just totally internal, and then we also have some combinational logic. So the user only can see the output and the input, it can't see what inside the device, right? So this is the automata model for a finite state machine. Now the FSM example. So we have like input and output. So you can see this is a state A, B, C, and D with a circle. And then there is a double circle here, double line circle. That's actually the starting state, where the state is going to start. It can't start randomly. And also it has like input and output conditions. So you can see input condition are in the blue colors. For each of the state, it has some transition to other state too with the arrow line. And also like on input and output condition. So you can see the blue one all are the input condition, and the red one are actually the output condition. And here the states are A, B, C, and D. So what we can do, we can from a state, for example here from the state A, we can go to B, but we can't go to C or D. From the state B, we can stay at B, or we can go C. Again from C, we can stay at C or can go to D. And from D, we can stay at D or go to A. So this is the condition. So suppose if the input is up and the output is off, that means the next state would be A. So if the present state is D, the next state would be A. So in that way, the state works. So this is actually the transition diagram for a circuit, okay? Now there's an example. Since in the last example we have only 4 states, let's represent those states A, B, C, D with the binary like 00011011, because at the end we need to design them in digital logic devices. And now suppose input is 0 for up and 1 for down, and output is 1 for on and 0 for off. And suppose this state A represented by 0 0, B is 0 1, C is 1 0, and D is 1 1. Now before starting, so this is the state diagram for a finite state machine. So before going to more in deep, let's know about Mealy machine and Moore machine. Actually, there are two types of finite state machines. One is the Mealy machine, other is the Moore machine. So Mealy machine, it is the automata model for a Mealy machine, where you can see that the output depends on the kind state and the input. So if the machine's output and also next state depends on both the kind state and the input, we call that a Mealy machine. But for the Moore machine, the output, you can see the output only depends on the kind state. But nexus can be a function of both the input and the kind state. But output is only depends on the kind state. It doesn't depend on the input. Then we call that a Moore machine. So this is the state diagram for a Moore machine. So we can see that the output doesn't depend on the output can be on or off. C or A off, B on, D off, C off. So output doesn't depend on the input condition. Output is, if the state, it depends only the kind state. So if the state is A, it's off. If the state is B, it's on. If the state is C, it's off. If in the state of D, it's off again, and so on. But the next state, let's suppose B. So next stage B depends on the input, like down, and the past. So the next state, like suppose you are in A. So next state B depends on the kind state A and the input. It should be down if you want to go to B. If it is up, if the input is up, it's gonna stay at A, and so on. For the Mealy machine, here we can see the output depends on the input too. So if you are in A and you press the input up, then the output will be off. If the state in A and the input is down, then the output will be on, and the next state will be B. Consider the state C. So if the input is down, if the present state is C, if the current state is C, and the input is down, then the output will be off, and the next state will be D. Similarly, if the input is up, the current state is C, and the output will be off, and the next state will be C again. So this is the transition table for a Mealy machine. So we can see the difference between these two. For Moore machine, so the output are inside the circle, right? The off, on, off, on. But for the Mealy machine, the output is with the input, because the output now depends on both the current state and the input. Now, let's create a logic circuit for a serial adder that actually add to infinite input bit stream. And stream are sent with the least significant bit first, LSB first. So suppose this is the adder. So we have like 2-bit stream, it's coming, and we need to add from the LSB first. So first we need to add what is 0 and 1. So we know if we add binary 0 and 1, the output is 1 and carry 0. You can see here. And then for the next stream, sorry, I need to make some correction here, because it should be like there. It moves somewhere. Okay. again we can see like here. So in the next state, if the value if the next stream is 1 1, so we know if we add 1 plus 1, the sum is 0. And what is the carry? Carry is 1. Carry out is 1. So I just write here with the blue line, so carry is 1. And then okay, and then for the third one we can see we have a carry 1, right? So carry 1 plus 1 plus 1. So 1 plus 1 plus 1, output is 1, and the carry is what? Carry out is 1 too. So in that way it works. So we have like we need to design with the FSM machine, right? So first question is, how many states we need to represent the finite state machine? 1, 0, 1, 2, or 3, or 4, or 5. Okay, so before telling you the answer, so we have some strategies to building a finite state machine. First we need to draw the state diagram, and then the highlight. Okay, so we need to draw a state diagram, then we need to write the output and next table, and then we need to encode stable states, inputs and outputs as bits, and we need to determine the logic equation for next state output, and then we need to draw the circuit. So how many states? There are actually 5 different states. So there will be actually 2 states. One for there is no carry in, other for there is a carry in. So look, we have like 2 input A and B, and what output we have? We have output Z. So the Z is the sum of the inputs A and B and the carry in, 1 bit at a time. A carry out is the next carry in state. So we have like 2 input, right? And here we know that the output Z depends on what? Depends on the input, because we are doing we are adding, right? So actually this is a what machine? Mealy machine or Mealy machine? Is the Mealy machine. So here we have 2 state. So here is the state diagram. Like if the input stream 0 0, then what would be the output? Output will be 0, right? And it has no carry. So S0 for carry 0 and S1 is carry 1. Okay. So if we have 1 0, so if we add 1 and 0, we get output 1, but no carry. So we are staying here at S0. Again, if we have 0 1, again with the output will be Z will be 1 with no carry. So we are going to state 1. But when we have 1 1, so that means output is 0, but what is the carry is 1. So we need to jump from S0 to S1 because we have a carry 1. Now we have a carry 1, remember. And then if the input is 1 1 1, output is what? Because we already have carry 1. So output is 1, and what I have? We have external carry 1. So we are still staying at S1. Now consider the next step. Suppose we have input A equals to 1, B equals to 0. And of course we have a carry 1. So if we add this, what we get? We get 1 plus 1 is binary, sum is 0, and carry is what? Carry is 1. So output will be 0 and carry is 1. So we are staying inside the state S1. Again, if the input is 0 1, output will be what? Because we have a carry 1, so 1 plus 1 equals what? Output will be 0 with a carry 1, so we are stating S1. But if both of the input are 0 0 0, so output will be 1 since we had a carry 1. And then for the next state, what? Output is Z1, carry is 0. So we need to go S0 from S1. So there is a transition. So this is the state diagram for a finite state machine when we are doing this real adder. So is this a Mealy machine or a Mealy machine? We can see here the output depends on the input. So this is a example of a Mealy machine. Okay. For Mealy machine, the output doesn't depend on the input. It only depends on the current state. It's a Mealy machine, so output depends on the inputs as well as the current state. Now we need to write down all the inputs and state combination. So we have like, so we need to write all the states 0 0, then 0 0 1, 1 0, 1 1, and then we need to write out which is kind state for them. So you know for S0 there are 4 defined states. For S1 also there are 4 defined states. We need to tabularize them. And also we need to write the output and the next state. Then we have only 2 states. Then we need to replace or encode each state's input and output as bits. So let's S0 equals to 0 and S1 equals to 1. So then we need to fill the table. So you can see the table from the previous state like this one, yeah. So from this is actually truth table right now. So we can build the circuit design using this one. So here is the so we need to determine the logic equation for the next state and the output. So this is for the output and this is for the next state. So we know for the z how many ones are there? 1 2 3 4. So from the truth table we are not using the k-maps, but yes, if the circuit is complex we still can use the k-maps to simplify the circuit diagram as well. So we are not focusing on the simplification now. We are just focusing on how to design a Mealy machine or Mealy machine, a finite state machine. So here we can determine, so from this we can have the equation of z and also the equation for the output state, and then determine the logic equation, yeah, and then we need to design the circuit. So what are the what are we going to cover? We're going to cover what we need to do. We need to draw this state diagram, and then write the output equation and next table, and then we need to encode the state, inputs and output as a bit, and then we need to determine the logic equation for next state and output. Today's class up to this one. Next class we will have the Mealy machine as well. Thank you.